One more factor that we have to consider when working with equilibrium constants and expression for equilibrium constants is that it depends on what state you have those substances. And all we've been saying so far is that we are working with the concentrations. But what if, for whatever reason, in that particular reaction, you have a substance that is in sort of a pure state? What I mean is, if you have pure solids or pure liquids in that reaction, normally what's going to happen is that you are going to completely ignore them. So you're going to leave them out of the equation. And why is that? Well, basically, if you have a pure substance, that pretty much is the maximum concentration that you can have at any given point. So past that, there is not much more that you can do for that particular substance to cause an impact on the reaction. So, for example, here in this reaction, you have that everything is either on the gas phase in aqueous form, or you have here in the liquid state. Okay, and this particular situation goes for liquids and solids. Okay, and remember, you are taking it out of the equation because the concentration of a pure substance doesn't change, right? So if it doesn't change, then you pretty much say it's constant, and as such it will be included in your equilibrium constant. So pretty much in this reaction you leave the water out. Okay, why do you leave it out? Because it's a pure substance. So pure substances, whether a pure liquid or a pure solid, normally they are left out of the expression of the constant. So in this case, it's only concentration of protons, concentration of bicarbonates over the concentration of CO2. That the proton and the bicarbonate are in a different state than the CO2, it doesn't really matter. Okay, yeah, the point is that on those states, either the gas phase or the aqueous phase, you can determine a concentration of each one of those species, a concentration that is susceptible to change. Okay, if they were pure, that concentration will not change. So in this particular case, technically, whenever you have that pure substance, it doesn't matter if you increase the amount of the substance. If it's already present as the pure substance, it will not cause an impact on the reaction. Okay, so here, if you have carbon here, there is no impact of that carbon being there. Okay, you can have a little bit, you can have a lot of carbon solid there. When it comes to equilibrium, the concentrations of both the carbon monoxide and the carbon dioxide is gonna be the same, no matter what you do with the amount of carbon that you have there. Okay, so that's the main concept behind heterogeneous equilibrium. Okay, so you leave the in this particular case, you leave the carbon out of the equation. So the equilibrium constant here is concentration of CO2 divided by concentration of CO squared. Why squared? Because you have a 2 there. The carbon solid doesn't appear in the expression. So, this particular case, it might look a little scary because now you have a solid here and you have a solid there. And you might be thinking, well, now what? Aren't you supposed to have an expression that is something over something? Well, yeah, but if you don't have anything to put that below the fraction, then there is no fraction at all. So for this particular case, Kc is simply concentration of CO2. If it was the other way around and you only have a reactant that is in the gas phase and everything else is in the solid state, then it's going to be the reciprocal. So let's say if the reaction was CO2 gas plus CaO solid, that goes to CaCO3 solid. I should change the color for that. So for that particular case, Kc is going to be, you forget about this one, you forget about this one, then is 1 over the concentration of CO2. Okay, it depends. It depends on what you have at hand. Okay. So pretty much in these cases, when you have a heterogeneous equilibrium, of course you may have to calculate constants, but this is more about understanding that when you have a pure substance, you leave it out of the equation. So here, water, it doesn't matter what the stoichiometry is on that one, you just forget about it. It's not gonna be in the expression of your constant. So Kc for this reaction, and then you have a fraction here. It's going to be the concentration of Cl2 squared divided by the concentration of HCl raised to the power of 4 times the concentration of O2. There is no water around that expression because water participates here as a pure substance. Things to consider here. Okay? So, pure substance. What are we defining as a pure substance? It's either a solid or a liquid. If you see a solid, if you see a liquid, then you are going to omit it from your Kc expression. Okay, you may argue this is a pure substance. Yes, it's a pure substance, but it's in the gas phase. In the gas phase, that substance, that pure substance, can change concentration. It's a gas, the volume changes. You can compress it, you can expand it. If you do so, then the concentration is going to change. Okay, but for solids and liquids, the concentration is not going to change no matter what you do. Of course, if you dissolve it in water, well, you are changing the state in that case. It's going to be in aqueous phase, and there is going to be a concentration there that could change. But if it's the pure solid or the liquid, the concentration will not change. So in this particular case, we are trying to, out of these three reactions, it could be one, it could be all of them, but we are trying to identify in which one of these reactions Kp is going to be equal to Kc. There is a catch though, because there is heterogeneous equilibria here. So how about we start by identifying what are the solids? And remember, solids or liquids, depends. Remember, the solids will not affect the reaction, and they will not count. So for example, this is a solid, and this is a solid. They will not count at all. When you are doing the counting of gas, number of moles of gas in the reaction, the solids will not count. The liquids will not count either. So we can completely forget about these two. And here, your delta N is going to be equal to 1 minus 2. Therefore, is equal to minus 1. And here, Kp, in this case, Kp is different from Kc. In the next reaction, iron solid, iron oxide solid, and then we have two gases here. Delta N is 3 minus 3 equals 0. For this reaction, Kp is equal to Kc. Okay? And we go through discarding those two. Last but not least, this is a solid. This is a solid. So delta N here is 2. Well, you can say 2 minus 0, so equal 2. So in this case, Kp is also different from Kc. Okay, so again, solids and liquids, if you have a problem in which you have to calculate Kp from Kc or vice versa, so solids or liquids will not be counted as moles of gas. Okay, so that just to keep in mind. And that's it for now.